Hello, everybody. Welcome to the Advanced Manufacturing Summit session on tips and tricks for generative design. My name is James Neville, and I'll be taking you through a brief presentation here today to go over some of these tips and tricks. So a little bit about myself before we get rolling. I'm a principal business consultant for Autodesk Global Consulting Delivery. It's a long title, but basically I assist and help our customers with adoption for a series of products, mainly our advanced design and manufacturing products like generative design, CFD, some of our other simulation tools. I joined Autodesk in 2011 through the Blue Ridge Numerics acquisition. Blue Ridge Numerics was the maker of CF Design, if you can remember back that far. CF Design was a CFD tool, obviously, designed for multitasking mechanical engineers or multitasking design engineers. So really folks who weren't experts in CFD or weren't experts in simulation, but needed to leverage the power of a tool like that or those type of simulation tools to make design decision. Sort of an upfront simulation approach to the simulation world. I joined Blue Ridge Numerics in 2005. And I started using CFD a couple years before that, using the CF Design product in college. So I started probably in around 2003, and really I've been focusing on CFD and related technologies since then. So I've spent pretty much my entire career, focusing on that sort of a technology. So I guess you could call me a simulation guy. I do dabble in all other forms of simulation. Fortunately, here at Autodesk, we have an almost ridiculous amount of technology that spans such a huge range of tool sets. But now, in my current role, I do focus mostly on CFD and generative design and some of the newer technologies that are centered around CFD and generative design. Some exciting stuff coming around the corner in the future here. All right, so let's get into the good stuff here and the reason why everyone's joining the session. So we are going to discuss some generative design tips and tricks. I have a small smattering of topics to cover here today. I do want to go over sort of like the basics, just a brief interface tour, just general conceptual strategies, why we do generative design, just the basics. I think it makes sense to go through an overview of that. I have examples for each one of these topics, but we'll then get into preserve and obstacle guidance. I think this is one of the first and most important things to learn about for gen design. Definitely want to cover synthesis resolution, the resolution of a study. A lot of folks have questions around that. And then we'll get into some more advanced topics like starting shapes and T-splines tips. Maybe we'll cover hollowing if we have enough time here. This is a small smattering. I only have, besides the basics, 4 or 5 things to cover here, but I will be interjecting little tidbits here and there along the way. But you could easily run an entire week of tips and tricks sessions around any of our tools, and gen design is no exception there. So I've just picked a couple of the more commonly asked about topics with gen design. And really, if you're, a starting user or even a medium experienced user, these sort of topics are the ones that are probably going to pop up first. There's definitely some more advanced things that we could get into, but that would probably, I think we probably want to do a whole other session on that. But I will be, covering these here, and hopefully have some good Q&A at the end, and we can follow up with anyone else if you want to get really in depth and get more advanced with your Q&A and question sessions. All right, so let's get into the first topic here and the basics. I'm going to just go over a sort of a brief setup overview. We'll do an interface tour. We'll look at the sort of left to right approach in the toolbar at the top there. So, the edit model workspace, the design space, looking at design conditions and criteria, materials, and then ultimately, previewing and hitting that generate button. Let's go ahead and jump into Fusion here. Pull up my Fusion window. So in Fusion, there's a series of workspaces here. I think everyone's probably mostly familiar with these workspaces, but this particular model, this is the GE bracket from the generative design sample section over here in the lower left-hand corner of my screen. If you haven't run through these design samples, or if you haven't done any gen design training, I highly recommend going through them. These little samples are, I mean, they're super straightforward. They run really quickly. There's some even more in-depth and better examples in some of our self-paced learning and training material. We could definitely point you to that. But for today, I'm going to be using actually some of these samples as some of the test models here, because they're just so simple, and I think it'll illustrate the points that I'm trying to show everyone. I'm going to go ahead and get rid of my hide data panel, I'm going to hide the data panel here just to make the screen a little larger for everyone. And basically this, you can see the parts here. There's a couple, pins here, or, preserved geometry. We'll get into some of the details on preserves and obstacles in a second, but I'm going to jump right over into the generative design environment, and we'll take a look at the interface and the setup here. So first things first, on the left-hand side, you can see in the upper corner, we're just going to go left to right and just run through basically the setup of one of these, just so everyone knows a full understanding of what all this stuff is. In this first pull down, you can see that there's study settings. This is where we control the synthesis resolution, basically the level of detail of the generative design study. If you've ever done any structural analysis or FEA, CFD analysis, anything with a mesh, this is the mesh. And we'll get into this a little bit later. There's actually a whole topic on synthesis resolution, but how you control this is right up here in the study settings. The next section here, this is a super important one. This is the edit model workspace. And this is a little abstract, because when I click this, this is going to take me into a workspace that looks very similar to the design workspace. You have edit model solid, edit model surface, just like in the design workspace, how you have solids and surfaces. Now, why do we have it sort of buried or one level deeper in the generative design workspace? So sometimes, and this doesn't just apply to generative design, but it definitely applies to simulation models as well. But sometimes we're working on an assembly, and that assembly is also being worked on by other folks, and we have to make modifications, or we might want to make simplifications or edits to that assembly to get it properly prepared for simulation. That could be removing some fillets for a CFD analysis, or it could be adding in some geometry for a mole flow analysis, or there's a number of things that we could do here. And if you do that to the design workspace, or the model at the design workspace, those edits are at the top level. Everyone sees them, and a lot of folks they don't care about that stuff. They don't need to know that you used a command to automatically find all the small holes and fasteners and components that are under 0.5 millimeter in total size and got rid of them. Right? They don't care about that. So this is a sort of a sub design workspace. We call it the edit model workspace, and it is buried one level deep. So it's in the generative design space. So anything any changes that are made to the original model, like the master model at the design level, will propagate through to the generative design edit model workspace. However, any changes that are made at the edit model workspace will not go backwards to the design workspace. That's an important distinction. But this model is sort of already prepared from the design workspace. It's already been prepared. We already have some obstacle geometry, some preserved geometry. We don't have the original GE bracket geometry here. It's already been sort of removed. In the future, if you were starting with a bracket geometry, maybe you would bring that into generative design, then go into the edit model workspace, and then make your edits, cutting out a preserve or defining what an obstacle would be. So I think that would be the sort of the preferred method as you go forward and make edits to geometry for generative design. Not to go into too much detail here, this is some pretty basic stuff here, but there's all of your creation tools, your modification tools. There's a really neat remove feature tool. This is something that's shared not only in this edit model workspace, but also in the like the simplify workspace in the simulation mode, you can come through here and use this, remove features command to automatically find, whatever features you have selected here. So right now it's looking for all this stuff, but it's going to find this stuff, and you have the opportunity to just, in one fell swoop, just delete it all, right? So a pretty elegant way to very quickly defeature and make a geometry a lot simpler if that's what you're going for. Let's go ahead and exit out of the edit model workspace. Actually, I'm going to cover one more thing real quick. Almost forgot. In the edit model workspace, you'll notice that there is like a submodel here. This is a generative model 1. So if there are multiple designs that we want to look through, maybe if we want to investigate generative design with different size preserves, or we want to move some of these obstacles, or test the difference between multiple preserve strategies, which I'll show in a future topic here today, you can clone this here. You can clone this design and actually have a whole nother like unique design, so unique CAD approach to generative design. So when you exit out of the finished model or the edit model workspace, not only would you have generative model 1, but you'd also have another one here underneath that would say generative model 2. So you could in fact investigate 2 different design approaches, so 2 different CAD models all in one generative study. For this GE bracket, we just have one CAD model here, hence the single design level right there. Underneath each design, you have at least one study. So I actually have 3 studies here. These studies, again, can also be cloned. Each one of these studies has a unique set of parameters here defined in the top toolbar, right? No, they all share the same geometry because they're under the same, design, the same generative model 1, but they have different approaches. So as we go through, and I'm just going to look at this one here, this top one, you can see that even underneath individual studies like this one, there's a bunch of load cases. Okay, so just starting to drill down through and show you just the level of detail that's going on here. So we've covered the edit model workspace. We've looked at the browser over here to give just a brief overview of what's going on there. The next one here, working our way left to right. This is the design space. So this is where we define what is going on with the generative design space. So this is just the environment in which generative design is going to work. We need to define our preserved geometry, right? Those are the things they're fixed in stone, and this is where we assign our loads and our constraints. Loads and constraints can only be defined on preserved geometry. So if you're trying to build a bracket or a bridge, you need to define, where that bracket or bridge mounts to something else, right? Those would be preserves. Obstacle geometry, this is, what block, these are blockers, right? So we're defining where the generative design space cannot go. We can go right up to it, but we can't go through these parts. So this is to avoid interferences, to make sure we have proper clearance with a moving part. In this case, there's, pins and, fasteners and stuff with this bracket. We have to define that explicitly. Otherwise, generative design will take whatever liberties it can, and it will build into any area that it deems necessary to achieve the criteria that you set. You can also define a starting shape. I have another topic on that in a little bit. But you can define a starting shape, and then there's symmetry plane here. This is showing up because I have some tech preview features on. I'm not going to cover any tech preview stuff here today, but that's why we're seeing that there. The next one here, design conditions. Structural constraints, this is a simple one, fixed constraints, pin, frictionless. If you're familiar with any structural analysis or FEA in Fusion, this will make perfect sense. For this particular example, we have some fixed constraints on these 4 like pin bodies at the bottom. And then the next one over here is the structural loads. So this is where we define what we know about the model. So if you have a force or a pressure, bearing load, moment loads, any of that stuff, this is where we define those items. Let's talk just a moment about load cases. So as you start to define these loads constraints, they will get summed up over here on the left. It is a good best practice to fully understand all of the various loads that your design is going to be subjected to before getting started here. If there's a load that comes in from like the negative x-axis, maybe occasionally a load that comes down from the positive z-axis, each one of those individual load cases or loading scenarios should be assigned in a unique load case. It's best not to add them all to one load case because we do some adding and subtracting, and if you put two opposing loads in one load case, those loads will cancel out. We take the effective load per each load case, and that is what is actually assigned and what drives the generative solution. So each load scenario should really be in its own load case. What all should you include in a load case? I mean, and try to keep. I think a good rule of thumb is to try to keep all of your load cases within like the same order of magnitude. If there's like for instance, this bracket, if there's a lifting force of, I'm just throwing a number out there, like 1,000 pounds, and then maybe a side twisting force of 500 pounds, like those are, basically within the same order of magnitude. If there's another load scenario where this thing is, I don't have a good example here, but if it has like 5 pounds in a different direction, that 5 pound load is it's so much smaller than the other loads that it will effectively be canceled out and won't even be part of the generative study. It's not that it's not important. It's just, I mean, it's not going to have much of an impact. So we don't have to take into account that sort of stuff. But definitely take into account the big stuff. I mean, if you know of a load, you should probably take it into account. One more note on loads. Some of these devices, and I found this out with some of my generative additive 3D printed parts that I've made. I have often missed a few loads. So I might know. I've built a bracket where it has to support a certain amount of load in a direction, and maybe there's some side forces sometimes, and I'm assuming that these like maybe these pins are fixed in place. But during installation, I've found that these pieces aren't fixed yet. So I'll go and I'll start fastening one, and then I'll start fastening the other, and I'm realizing that I'm flexing this plastic part like just incredibly. So that's a loading scenario that I didn't often think of, installation loads and handling loads before I'm able to actually, fix a bracket to a wall or, fix one component to another. So just another, you just got to sort of step back just for a second and, make sure you're taking into account, all of those different loading scenarios. Moving on, the design criteria. This is where we define what generative design is targeting. So first and foremost, we're defining objectives. So you're either minimizing mass or maximizing stiffness, and you get to define your safety factor. If you have some of the advanced solver or tech preview solvers on, you might get some additional stuff here, like you can solve for modal frequency, and you put in some like displacement and buckling limits here. Again, tech preview stuff, so I'm not going to go into that. But this model actually does both objective targets. So we have both the minimize mass and maximize stiffness. So if you're going for minimized mass, it's going to try to get your generative part as light and as small as possible without violating that safety factor of 2. So it's basically going to try to get a safety factor of 2 everywhere on the generative model, which is nice. If you switch this over to minimize mass, you put in a specific mass target. So maybe you want to get it down to 2 pounds, but you want to have the absolute strongest part at 2 pounds. It won't let any part of the geometry get below a safety factor of 2, but it will try to make the model as strong as generatively possible for a specific mass target. So two different approaches. This model actually has both approaches. So the first study over here is minimizing mass, and then there's 2 mass targets of 1.5 and 1.8 pounds. The next one here, manufacturing criteria. This is where we define the criteria that drives the generative study. So these are sort of additional criteria, and you can turn them on or off, but not to go into too much detail. I know we only have an hour here, but this is there's a number of different options here. Some of these are tech preview options like die casting. But yeah, you can turn these on and off. Today, I'm primarily going to be looking at the unrestricted outcomes, just to go over some of the general tips and tricks on generative design. But yeah, there's some additional outcomes if you want to take into account more of the manufacturability criteria of your generative design. Materials are pretty straightforward. If you want to use a material, have a material included in the generative study, simply find it in the library and just drag it and drop it up into the study. We do have an additive library that is full of materials that are specifically designed for additive manufacturing, but you are not exclusively limited to these materials. You can put in anything. So oftentimes I'll go into the Fusion 360 library and then go to plastics and bring ABS plastic in there because that's a common plastic used for say like 3D printing, ABS, ASA, stuff like that. Going on to the generative or the generate section here, you'll see a pre-check. And if you have any issues with your model, I have a flag on. That's why you see this little caution symbol. But if you have any issues, they'll pop up here and you can resolve those. I'm going to put in a plug for the previewer. This actually spools up a partial generative study locally on your machine. So it actually does an unrestricted only analysis locally on your machine. You can't do anything with it, but it is a previewer. And like, why would you have it if you can't do anything with it? You might ask. Before you hit the solve button or the generate button to send your generative design study out to the cloud, definitely run the previewer, because if you get a failed message at the previewer level, you will also get a failed message at the generative like cloud solve level. And if a solve failed, it's not going to charge you, but it is going to waste your time. You're going to be waiting there for a few minutes or 30 minutes, an hour, depending on how big the model is, just to get a message that says like something failed, right? So if there's an issue, you can troubleshoot it here right away with the previewer. Plus, it just kind of looks cool. This thing runs in real time, actually. So if I was going to like make changes to any of my parameters, add a new case, whatever, it would update this previewer in real time. So definitely take advantage of the previewer. It's really powerful. And then finally, the generate button, pretty self-explanatory. All right, so now that we've covered the setup environment for generative design, let's jump over into the explore environment. So here we're going to discuss filtering, display modes. We're going to look at how the outcome progression works for all of the outcome iterations, and then ultimately how to get an outcome out of or a design out of a generative design outcome. Again, we'll fire up Fusion here. To get into the Explore environment, once you have results that are solving, or after the completed, you'll get access to this Explore Generative Results workspace. Let's go ahead and click that. And the first thing you might think when you see this is wow, I have a lot of stuff here, and I don't really know what I'm looking at. So this first image it's giving, or this first workspace view, it's showing you thumbnail images of all of the outcomes. Each one of these is a unique outcome based on the number of studies that you have, the number of materials, manufacturing methods, all that stuff, right? And it might make sense to talk about filtering here. So if you look over on the left-hand side, these are outcome filters. You can see that I have 3 different studies, these 2 different mass target studies. Maybe I want to just isolate on the minimize mass study for there. So now I've just cut out 2/3 of the studies. This is a little bit more manageable here. We do have a visual similarity grouping algorithm that we run. So this will group similarly looking studies together. I'm not going to play around with that one right now, but that's an interesting feature. And I do have some tech preview stuff on, so I'm going to turn that off. This will dramatically reduce the number of studies here. So again, we're just covering the non-tech preview stuff. Manufacturing method. This study did have additive and unrestricted. I'm just going to look at the unrestricted. So we're really drilling down to some of the more specific studies now that we're looking at. So now I've just got 3 on here, and these are organized by the material grouping. So you can very quickly use this filtering mode on the left-hand side of the screen to drill down and get a better understanding of just a small subset of your entire generative design study, as opposed to looking at the whole thing at one time. There's other ways to visualize this. I'm going to turn all my filters back off, except for the tech preview. I don't really want to look at that one right now. And if you look at the properties of the different display views at the top of the screen, so this is the thumbnail view. There's the property view. It's basically extended thumbnails, right? So it's giving you information about each study. Sometimes it's easier to see this you don't necessarily know which orientation of additive study you're looking at, or which specific manufacturing method or material you're looking at if you're just looking at the the thumbnail images. There's a scatter plot view. This is a really good one. I'll pause here for just 1 second. Here we can illustrate on a graph all of the different outcomes. So I've got on my x-axis mass, and on the y-axis you can see minimum factor safety. Now we're targeting a factor of safety of 2 for all of this, so I would expect them to all be about the same, and they are. But maybe we can look at something else like piece part cost, right? Or fully burdened cost. So you can illustrate these things and quickly find out, why are these ones all the way over here? This is 440 steel. Is that they're a little bit higher than this titanium? Is that actually more expensive? I don't know. I don't know much about 440 steel, but maybe you want to look at max displacement. So this is displacement in inches, and typically you can find these parts grouped, and they are. So color coding at the bottom, you can change how the symbols are illustrating the data. So I can see that all of my 440C stainless steel materials are down here. So additive and unrestricted solutions are all around the same mass and displacement. And then my 446 steel, those are also around the same mass and displacement. I can see titanium all the way over here on the left. That's the lightest of the materials here, and those also have similar mass and displacement. And so just another way to illustrate the data here. Let's go ahead and drill down into maybe one of these studies. Let's take a look at this one here. All right, so now we're looking at a specific outcome, and this particular outcome you can see is so it's a stainless steel outcome. It's unrestricted. At the bottom of the screen, you'll see a slider, right? This moves back and forth, and this basically takes you through the iteration progression. So as you start moving forward, you can see how the generative progression works. And as we're getting closer and closer to our factor of safety target, this will get smaller and smaller, and then finally it'll reach its solution over here at the end. Any of these studies are viable, or any of these iterations are viable, and any one of them can be exported out into a design. When an outcome has been created, by clicking this button right up here, Design from Outcome, when that outcome is ready to be consumed, you can go ahead and click this green Click to Continue button, and your outcome will pop up here, right? So this is a design created from a generative outcome. And this is actually a new part now. So you look over on the left-hand side of my screen, I've got my original generative design study, and I've got this bracket outcome design file. So I'm in the design workspace. This is no longer a generative design workspace part. This is just plops you right into the design workspace. And what you're looking at is a final product out of generative design. In the lower left-hand corner, I think this is an important thing to cover. You do have some timeline data here, so I'm going to go all the way back to the beginning. Step 1, it brings in certain bodies, the preserved bodies. So you can see all of the various preserved bodies. So you can really step right through the progression of what generative design does when it builds this outcome for you. The next step is to bring in your obstacles. You can see that I have several obstacles here. The ones that go through the pins, and then this one that goes through the sort of that mounting bracket there at the top. Next step here is to bring in the actual form body. So this is the T-spline, form shape here. That's an organic, just a surface body, right? It does interfere and connect up to our sort of interface into our preserves. But you can see the different bodies there. Next step is the boundary fill operation, and the boundary fill is a cool one because it does sort of it's kind of like a surface wrap, or a way to combine surfaces and solids together, at least as far as like the outer boundary is concerned. So since this form body slightly interferes with all of our preserved geometry, we can use this boundary fill to create essentially the final generative part. And then the last step here is a combine command, where it actually cuts away the existing obstacles from the body, just to ensure that there's no interferences. You can actually see the impact here, where those obstacles actually just slightly interfered with the generative shape. I'm not a huge fan of this, and I've got a workaround of how to avoid this. But I think it's a good thing because it ensures that the generative part truly adheres to the design space settings that you've set forth when you hit that solve button. All right, so let's move on to some tips and tricks for preserves and obstacles. I think this is one of the One of the biggest areas for tips and tricks, I think, because this is really the foundation of the generative study, is where the preserves are, where the obstacles are, and how that resultant generative shape is going to interact with them. So I've got this neat little example here. There's two little steel rails, and there's like a control unit, like an engine ECU or an accelerometer, some sort of a sensor that is mounted sort of above and in between them. And we need to build a generative part to replace like a sheet metal bracket. So let's take a look at this example. I have two different images here. The top image shows like a very geometric approach to the preserves, where you can see that is sort of a cylinder. A lot of our examples have this, and I think this is sort of like the easiest thing to do is make a preserve that's very geometric. But I've found that at least if you're using the form based generative outcomes like casting, the additive outcomes, unrestricted, these are the CNC, the 5-axis milling outcomes. You get a very organic generative form shape, and I think it is helpful to have rounded corners on many of your preserved geometries. They don't have to be huge, but I've found that the generative form shape seems to match up a little better, and it's a little easier to post process, maybe add stress relief fillets or something like that in post if you use a rounded approach there. Just a general tip and trick, and I've got an example here that we'll go in and show that in a second. Another one is obstacle offsets, and you saw this with the GE bracket that I had up on screen just a second ago. I'm not a big fan of that final operation in the generative design like outcome, where there is a combine command that has to remove any remaining material or interference material that the generative part has made with the like the obstacles. I prefer to just like never have any interference at all, right? It's not that the command is bad, it's just I prefer to fix that upstream as opposed to downstream. I want the generative part to be whatever was generated and not to be modified afterwards. And also some of those cuts can sometimes lead to, some stress rises or stress concentration. So I definitely want to avoid that. So this method, if you look from the bottom, you can see that I've got some obstacle geometry for like access for bolts and tools and stuff to work the generative preserve into the sheet metal part, and then you can see the actual like sheet metal obstacle all the way at the bottom there. Notice how there's a slight offset. So what I've done is I've actually used the offset command in Fusion to just pull the sheet metal obstacle parts just slightly into the design space. I think this was like a millimeter. It's not even that much, but it just gives a little bit more breathing room, and it allows that generative part to go right up to this sort of like an offset obstacle as opposed to the obstacle itself. So if there is, and there is a chance that the generative part will like slightly go through that obstacle offset, when the generative part is finally brought back into a design and we go to do an interference check, there's almost no chance that it will be interfering with like the original sheet metal part there. So I think this is a good thing to help avoid that, any stress concentrations from that final combine cut, or avoid any potential like vibration issues if there's going to be some unwanted contact between the generative part and any of the other obstacle geometry. So just a little tip and trick. I mean this is applicable for almost every generative study that we set up. If there is an obstacle that you're trying to avoid, it can help to set your generative obstacles with a slight offset, just to help get a slightly better outcome. And you're sort of taking into account, or you're taking care of that potential interference at the setup stage, as opposed to modifying the form body at the post stage, which is quite a bit more difficult and time consuming. So let's get into an example here. So I'll fire up Fusion once again. So here you can see my my control unit bracket, or control unit example here. I'm going to jump right into generative design and just go over the setup here. So I'm going to get into the edit model workspace. This is where I set up my preserves and my my obstacles. So I have two designs here now. Instead, the GE bracket, we had one design. Now I have two designs. So I had actually made the first one and then cloned it. So I have baseline and then optimized. So the baseline design has a very traditional approach to these obstacles. They're very geometric. They're sharp. There's sharp edges on them. The obstacles themselves are built directly off of the sheet metal from the original geometry. Okay, so there's no offset. When I switch over into the optimized mode, you can see that there's a slight offset here. Let me highlight the offset command so you can see this. Go ahead and edit this feature. So you can see right up here, I had selected that surface and actually pulled it down. Pretty easy when you have something like this. It could be more complex if you have a very complex set of obstacles. But for something like this, that offset is quite easy to do. You just select all of these surfaces here and just pull them up. I think it was 0.5 millimeter or a millimeter. You can also see that I've made some changes to the preserve itself. So I've rounded this top surface. So basically, the landing zone, the area where the generative form shape is going to come down and build to, is always curved here. There's no sharp edge. So that's going to make adding a stress relief fillet afterwards very, very easy. And this is the sort of just a tip and trick for getting a slightly optimized or a slightly more optimized generative outcome at the setup stage, as opposed to doing this all at the sort of the post processing stage, if you will. All right, so let's take a look at one of the outcomes from this control unit bracket study. This is one of the baseline outcomes. So it's it's an unrestricted outcome, which is why it looks so organic and spindly and natural looking. But it's a cool outcome. But this is the outcome from the baseline study. So without those optical offsets, without the rounded preserves. And I want to highlight a couple of areas, and I'm going to easily do this by selecting the combine cut command. This shows everywhere where the model has been cut away by the obstacles. So you can see it actually went right up to the top. Portion of this went right up to the top and actually touched the underside of that control unit, which I don't want. I want my contact at the mounting points, not anywhere else. So that's not good. I don't see any contact on the bottom side. So it actually stayed off the sheet metal pretty well. But I see an egregious gouge here, actually two of them. The access obstacles to like for tool access to reach the bottom of this preserve, you can see it actually gouged out a pretty good chunk right there. That reduced like maybe 15 or 20% of the thickness of this particular member, this portion of the generative study. So let's take a look at the stress analysis and see the impact of these assembly cuts. So here I am in the simulation environment. Of course, all of your loads and constraints come through from generative design, which is super handy and time saving. Let's go right into some results here. So this is looking at some of the loads here. You can, again, go through all the load cases. But if you look at the Y loads, so that's the load from the like the left-right direction. Check it out. As we look at a stress plot, the areas where you get stress concentrations, this doesn't always happen, but right here, like because of that gouging, like this is now a stress concentration. This is significantly higher stress, like 2x more than the surrounding area because of that cut, right? So these are things that I typically try to avoid, and taking that offset approach to your obstacles can really help avoid this type of problem. And I think it's a good thing. And this is pretty clearly illustrating why you don't want these sort of interferences or these sort of clashes. I don't see too much of an issue on the top. I actually don't see any stress concentration at all with any of the load cases in this cut. You can see this sort of lake-looking shape one here. That's the remnants of the assembly cut there. I don't see any stress there, but this this control unit, when mounted on this bracket, if there's any vibration, whatever, this is actually going to touch here too. And is it going to be a big deal? Maybe not in this case, but for some models, absolutely, that could be a source of additional load, or maybe a sometimes in contact transient or vibration load. So typically things that we want to try to avoid. Let's take a look at the optimized study here. So this is a comparison of the optimized. It's a comparison of the optimized outcome with and without like stress relief fillets on the region where the form body comes down and touches the preserves. So I'm going to do a compare view, like a side-by-side view. And on the left, I'm going to have I'm calling it simulation model 1. That does not contain any stress relief fillets. And on the right, we've got simulation model 2. Yeah, let's take a look at the same load case here. Again, let's take a look at the Y loads. And just zooming right in here, you can see there are some specific regions around this geometry where we get stress concentration, namely at the location where the form body comes down and intersects with the preserve. And so in a region like this, you'll notice that on the right-hand side, I have a nice little fillet there, just a really small fillet, something that can be either machined or additive manufactured. This sort of fillet helps to spread out that load, and you don't get those sharp edges. You still see there's a concentration now, but it's now spread out over a larger area, as opposed to this like sort of point concentration here, which could lead to like a crack or a failure. We definitely want to relieve stress around these where possible. You'll notice that both of these studies, these are done with the optimized outcome or the optimized generative setup. So we do have our rounds here. Notice this, the way that the generative form body comes and intersects or interfaces with the preserved geometry, it happens along like just one continuous line. This is not the case if you don't have these sort of rounded shapes on the generative preserve. The round does not have to be huge. This round here is actually quite large, just for illustration purposes. But even a small fillet on your preserves can help dramatically in post when you go to add some of the stress relief to your final generative shape. And then one final comparison between the baseline generative setup and the optimized generative setup here. I've incorporated both of these designs back into an assembly with the original control unit assembly as well. So looking at from a side view, you can see this is I'm just looking at the original control unit and now the baseline generative design study. You can definitely tell the form body gets really close, really close to that sheet metal part, which I don't particularly like. You can see that there's no room to even add stress relief. And sometimes this will actually like just be flat with that. So you get these like little tiny edges that are, they're just tough to work with afterwards. Can you work with them? Of course, but it's just easier to handle them in pre-processing than in post-processing. Same thing over here, really close. We don't actually interfere with the sheet metal part, which I just went over a couple minutes ago, but I have seen a similar study like this where you'll see this shape will actually just follow the exact line of like this particular optical surface, which is, to be avoided. I see almost no light at all between the control unit and the top surface of the generative part. In fact, you can see it's actually contacting in some spots. And, is it going to make a big difference with this one? Probably not. But for some models, absolutely it could. So let's go ahead and swap this one over. So I'll get a nice side view so you can see the swap. And let's turn on the optimized run. The overall size and shape of this thing, it is almost identical. It is truly almost identical. If you swapped back and forth really quickly, no one would be able to tell the difference. All the members are in like almost the exact same size. You can see that you get that like sort of hatching that appears when you have surfaces that are like almost overlapping. The solution is so similar, but just in a couple areas, there's just like an offset, right? So if you're looking from the side view, I will turn off the baseline model. And now you can see there's just a healthy amount of breathing room between the obstacle and the form part. So there's room for me to, this has a bit of like room for flex, right? If it's going to bend a little bit, it's not going to interfere with anything else and then crack on a new stress concentration. There's room for stress relief right here. If I wanted to add a fillet right there, same thing at the top. So this is just a really good, tip and trick for pre-processing, or just something to take into account that can help before you even hit the generative solve button. All right, moving on to synthesis resolution. That's the resolution slider back at the setup phase, where you get to define essentially the resolution of the generative design study. There's 100 ticks on the resolution slider, and the default is 40. So you can see it's got like a not a percentage or anything. It's just it goes from 0 up to 100, and the default is at 40. So if you move the slider all the way to the left, you'll get a faster solution because it's going to use larger voxels. It's going to break down your design space into larger chunks. So there's less data and there's less math that has to occur, has to, less data is taken into account into the generative, solve process. You slide that thing all the way to the right, and the amount of data goes up a lot, and the speed goes down a little bit, and the total time to solution is going to go up. There are some specific high resolution applications where you'd want to have, the slider moved up, but I think in general you can probably leave it around the default. I actually like to move it a little bit to the left. I like moving it to around like 20 ticks on the slider bar there. But let's get into an example here, and I'll show you, sort of the impact of that resolution slider. So this is a study to look at just like a hanging bracket. So I've got like these 3 mounts that would like mount on a wall, and then over here on the right there's going to be like a pin with like a load that's going to be pulling down on it. Really simple, just one load case. I do have different resolution studies over here. So this is one generative design study, but I have 1, 2, 3, 4, 5, 6 of these things all in one big study. So I'm looking at different resolutions here. So a resolution of 0 all the way up to 100. Okay, so each one of these is taken into account. Let's jump into some generative results. So here is the generative design outcome for a resolution of 0. Okay, and typically what you'll find here is that when you move that slider all the way to the left, you get larger structural members like this. Which is sometimes desirable, right? You get larger structural members. It kind of avoids some of the smaller, like more spindly structural members, which in many cases is desirable, right? Because those are hard to manufacture. They could be points of failure for like certain vibration modes because they're so small. So I think this is it's totally valid to move that slider all the way down. You're not losing any like fidelity in the solution quality. It's just it's less data that is used, or there's less data or less volumetric data really available for the generative design study. It doesn't make it any less accurate. It's just when it's doing its sort of topology optimization work, you're going to result in larger shapes typically. So I think that's one potential reason to move that slider all the way to the left. Let's go ahead and look at something a little more higher resolution. So here's like say resolution 40. This would be like the default. So if you ran this with the default settings, you would get something that looks like this. The shape is still generally similar, but now we're starting to see more like, little windows open up, more spindles here. The part will probably, not necessarily, but probably be lighter because it's, there's more data in the design space. There's more area there's more volume really for generative to work with and remove. But you can see the general size and shape is about the same. But now it's, I'm using thinner members, right? The result is there's a thinness here that wasn't there previously. And if I get out of this mode and go into a comparison view, you'll be able to see this. Let's go. Actually, I'm going to show one more here real quick. Let's look at maybe resolution all the way up. So we'll go resolution 100. I don't recommend using the resolution slider all the way at the top. For some reason, and I think maybe with the way that we're doing the math on the voxelization, the solutions never really turn out that well. If you go like 95, like almost all the way up, you'll get a good solution. But I don't recommend using the slider all the way to the right. I typically don't get good outcomes there, but you do get pretty good outcomes almost all the way up. Let's look at resolution of 80 here. So this one is you're starting to see it's a little bit different. It kind of looks like a wing or like a bird flying here. Much thinner elements, but I don't have any like spindles. So at 40 at the default resolution, I had some spindles, but now here at 80, I don't. This is very application specific. You might see the opposite occur going from 40 to 80 or from 20 to 40 or 0 to 40. So I do recommend, definitely using the default settings and maybe one lower and one higher. And then you can, pick and choose between them. So let's take a look at a comparison view. Let's do 0, 80 here. I'll just do a compare environment. So see what I did there. I just clicked just to enable each one of these, and then you get a an option to compare these side by side. So this is, two solutions. Both of these are perfectly viable, but they are different outcomes, right? Just by looking at a different resolution. One might be better for a certain manufacturing method, and one might be, lighter. You can see that the one on the left is 2.33. That's the factor safety, 2.33. Got a mass of 0.016 kilograms. The one on the right, again, mass 0.016 kilograms, but my factor safety is a little bit lower. So, these sort of back-to-back comparisons can help you look at these different synthesis resolution settings and then pick and choose the one that works best for you. I have one other example. There are certain scenarios where you might want to use a higher resolution for your synthesis slider, and one is when you have really small preserves, something like this, or even smaller. I've got this little tiny ring with some loads on the outside. I actually was trying to make an example for this summit presentation, and I didn't have enough time to quite finish it, but I think the example is pretty poignant in that when you have really tiny preserves, you need more resolution in the design space to really capture them and to make the solution accurate. And when you go forward and look at some of the outcomes here, you can sort of see this in the results, that there's just not enough resolution. I didn't run a study that was probably long enough to really show this. But if you look here, some of these interim results, it's not even picking up. This is with a resolution of 0, so all the way at the lower end of the spectrum. It's just not even enough resolution to pick up that ring. That ring, the entire ring was a preserve, right? And there's a chance that it might be able to bring it back in the final outcome, but that's not always the case. So if you have these really tiny preserves, that's one other good area, or one other good reason where you might want to put that slider up into the maybe 60 to 80 range to get some more resolution, and hopefully capture that so your outcome doesn't look like this. All right, let's move on to starting shape. So a starting shape it's a good way to kickstart a generative design study. You don't have to use it. If you choose not to use a starting shape, it's perfectly fine. It's actually how I use how I set up most of my generative design studies. If you don't use one, Fusion Generative Design is going to basically build a block of volume or a block of material or around your generative preserves and your obstacles, and then it will start to whittle away from that, growing in some spots, but mostly just removing material where it can until it reaches your target criteria. If you put a starting shape in there, the one caveat is that the starting shape must connect or touch all of your preserves. But assuming you have a starting shape in there, the initial volume that generative design starts from is the starting shape, naturally, hence the term starting shape. You can imagine, and I'll show this with this example here on this simple bracket, same example we used for the previous tip and trick section. You can imagine that the initial shape or the starting shape is usually vastly smaller in volume than the non-starting shape approach, where it wraps a body around everything. So you can get to a solution much quicker with fewer iterations. But the big thing is that if you use a starting shape, it will absolutely influence the final outcome. You will almost never get the same outcome as you would not using a starting shape. And I'll show that with the example here. Another little thing you can use a starting shape for is that let's say you have a particularly large domain that you're working in for simulation or for generative design, and there is a hard limit in generative design to how much material can be removed during a study. I believe it's 95% of the volume, or 95% of the original volume can be removed. Once you reach that 95% volume reduction limit, generative design will stop, and it'll say that your study has been completed instead of converged. A converged study is when generative design reaches all of the target outcomes or the target criteria. A completed study means that the run completed, but it stopped for some reason, and the fact that it could not remove enough material to get down to a factor safety of 2 or whatever your target criteria was could be a reason to stop. So it is possible to take the finishing outcome, to output or create a design from an outcome, and then re-import that to the original generative design study, and then use that outcome as a starting shape to continue on. So you can actually use it to, you can kickstart a solution with something super geometric like this that I made with lofts, or you can kickstart a solution with like a previously run generative design outcome. So it's pretty interesting how that could be used. Let's jump over to Fusion and we will take a look at this example. So this is the same general setup as the last study that we looked at with synthesis resolution. This time we're just going to compare a study with and without a starting shape. So just to remind you what that looks like, here's my my generative setup without the starting shape, and then with it. And again, this is just something I made in the edit form environment. It's actually really easy to make. I just used a couple lofts, like lofted from this face to this face, and then basically combined them all together. I did add a couple fillets in here because, you know, why not? And yeah, let's compare these. Jump over into the Explore environment. So again, I'm just going to compare two studies here with one unrestricted study, manufacturing method. We'll look at, you know, a single material, ABS plastic. Yeah, let's take a look. So this is the outcome without a starting shape. So if you go all the way back to the beginning, it looks like something like this. I'll just turn on my preserve so you have an idea where they are. There's the obstacles as well. Okay, so there's that sort of kind of like it's not a bounding box, but it sort of draws a little bit of space around all of your preserves, and then, you know, does like the minimum volume to sort of straight line connect all of these shapes. That's your initial, you'll see this quite often if you don't have a starting shape, something like this. So let's advance through the iteration timeline at the bottom of the screen. Let's go maybe 10 iterations in. You can see the thing's starting to get a little organic, right? It's starting to remove material in certain areas, and you can sort of see that sort of that like triple member outcome starting to take shape. Advance forward. Let's go 30 iterations in. Now starting to get that sort of wing shape that we saw previously. 50 iterations. So that's a lot of iterations. 50 in. You can see now it's got that bird profile, that sort of wing shape that we saw. And then all the way at the end, this is your final outcome. You'll notice this looks very similar to the outcome that we saw in the previous example because it's the same, right? This is the default resolution. So that value of 40 on that resolution slider. Okay, pretty cool looking outcome actually. But this is you know, an unrestricted outcome with no starting shape. So there's no additional guidance or kickstarting involved. You can see that we're down to, you know, we've reached our target limit, or very close to our target limit, or sorry, our factor of safety target of 2, right? So we've gotten down to 2, but our weight is 0.016 kilograms. Okay, so that is one of the or this is the outcome, like the final outcome. And this did actually converge. So this reached our target criteria. All right, so let's exit out of this one and take a look at the other example. Okay, so here is an example, same exact setup. All we have different is a starting shape. Okay, so as we started to advance through, you can see the progression of the starting shape. I mean, naturally, the starting shape volume is much, much smaller than the original volume used without a starting shape. So there's 10 iterations, 20 iterations. You'll notice the other one went like, I think it was 62. This one only has 34, so it's half the iterations, right? So it's going to solve a lot quicker because there's just less material to remove. Already, you can see that we're almost at our factor of safety target. We're actually a little above where the other one was. We're 2.17, so it hasn't quite reached 2 yet, but we're at 0.013 kilograms. So the best or minimum weight, or the lowest weight that we could get without a starting shape was 0.016 with that particular, you know, methodology at that resolution. Let's advance to 30. So now we're at 0.008. We're half the weight by using a starting shape. And obviously this is, you can see it's much smaller, right? And then here's the final one. So now we're down to 0.007 kilograms. We still have our factor safety of 2. So we're satisfying our design criteria, but we have a much, much, much smaller and lighter result, right? We don't have that bird shape, right? It's a totally different shape, right? This almost looks like you could take, you know, some straight tube sections and weld them together and make something like this. You could not easily manufacture the other design, even though these are unrestricted outcomes, right? They're both unrestricted, just we've given one a massive head start with the starting shape. So you can see the potential value of using that And yeah, hopefully that makes sense, and how you can leverage a starting shape and why you might want to use one with your particular generative design setup. Time to get interesting with T-splines. So let's go over some T-splines tips and tricks and what I'm talking about when I say T-splines. So we're going to talk about basically the form bodies. So for certain generative design manufacturing methods, you will get an outcome that involves a form body. Basically, everything that's not like 2-axis cutting or 2.5-axis milling, you will get a form body. And these are those organic shapes like this, where you have like editable surface geometry that connects up to our preserves. So we'll talk about the reasons why you might want to modify a form body. A neat little trick using Alt. Holding the Alt button while moving or editing, which will add geometry as sort of a creation tool. Smoothing, I think that's a really important one. Preserve region continuity is absolutely critical for getting a good outcome out of generative design, or any outcome out of generative design. And then ultimately, we'll talk about the smooth and box view modes also. So let's jump into Fusion and get to the good stuff here. All right, so this is the Alcoa bracket example. Again, it's located in those generative design example files in everyone's installation. It does have a starting shape. You can see that, the big yellow starting shape. We just chatted about these. This model actually will not run without a starting shape, because there is no there's no like line of sight. There's no direct way for it to connect these preserves over here to this preserve here. So like without a starting shape, this one won't actually run, which is interesting. So you must run this with a starting shape. But this is the model that we're going to use for the T-spline workflow. So we've done our generative study, just advancing forward 30 or 40 minutes, and now we have an outcome. All right, so we're looking at this 446 stainless steel outcome, right? And much like we went through in that sort of the basics guide earlier, you've got your preserves, just going through the timeline at the bottom, your obstacles, the form shape or the form body there, the boundary fill to connect it all together, and then ultimately the combined cut, which, like I've said before, I'm not a huge fan of. At least I'm not a huge fan of when it needs to be in play to get a good result. But this one does have a combined cut in it, and yeah. So this is a decent result, right? This is something that you could run a stress analysis on for validation. Take a look at it, but there might be some things that you might want to change. So if you want to go back and edit this this form body, like how would you do it? Why would you do it? Maybe there's a stress concentration that you would like to like smooth out a little bit. Maybe you don't like some of these structural members. Maybe like this hole is not manufacturable. Maybe you're doing additive manufacturing and you don't want to have to worry about filling a hole in or removing material for support or whatever. So let's take a look at some of these methods to edit a T-spline, and yeah, we'll dig into some of that. So much like generative design, this session could be split into, you could split this into 10 sub-sessions on just T-splines. Like T-splines is kind of you're sort of one step removed away from even generative design. Generative design being one step, deeper into like Fusion itself. But T-splines is sort of another little tangent here. I think it's very powerful. It can be a little daunting at first because it's new and it's different, and people might not have dealt with form bodies before. But hopefully I can take some of those, or maybe dispel some of the myths and give you some general tips and tricks for using T-splines that will help you get a little bit more value out of the tool, have a little bit more confidence in using T-splines or modifying T-splines. One thing I'm not going to get into today is like just general creation of forms. Like there's a whole different, you could do another tangent of training material and tips and tricks on just creation. I'm going to focus primarily on editing or massaging an already created form body or T-spline body. So let's go ahead and look at that now. So in the timeline, you can either scroll backwards. You can leave your timeline marker all the way at the end. What I'm going to do is I'm just going to simply right click. You'll notice that I'm just in the general design workspace. I'm just going to simply right click on the form body in the timeline and click edit. This will take me over into like the form editor, the T-spline editor. Okay. And now if we go up to our bodies, you see that we're sort of in a, I don't see like preserves or bodies or any solid bodies. I have this organic shape, right? So I have one single organic shape here, which is my T-spline body. Let's take a look at it. So, brief tour. There's a bunch of creation tools here where you can, create, individual faces and lofts and sweeps and stuff. We're not going to do too much of that. I typically spend most of my time in the modify command. There's a lot of stuff here. It looks a little daunting at first, but most of these, a lot of this functionality can be boiled down to just like edit form, fill hole, welding edges, merging edges, erase and fill, like some of these, and smooth. You can look and you can really geek out with some of this stuff. But I'm just going to touch on just a couple of the primary ones, and yeah, we'll go forward from there. In the utilities tab, there's a display mode. I have it promoted to the top here. When you open this up, this will cycle between the different display modes, and really there's two that are most valuable. There's the box display mode and then the smooth display mode. And the smooth display mode shows what the T-spline is going to look like in final form. Okay, and that's what's shown by default. Everything's really smooth and swoopy, and there's a lot of curvature involved. If you enter into the box display mode, you'll see everything get faceted. So these are the actual control vertices, like the CVs of each one of these. All the surface bodies. You can see it's pretty smooth, but you zoom in up close and you've got it's faceted, right? Switching to the smooth display mode, everything gets very, very curvy. The location of each point, it's not like you're just turning on like Phong shading or Goralid shading or anything like that, where it's just, it's not a shading thing. This is at like the CVs actually change depending on which view mode you're in. So this one right here will be in a different spot when I go into the box view mode. It's a totally different spot. So I think it makes sense to edit sometimes in both of the environments. You do need to double check any edits that you make in the box mode just to make sure that, they work well in the smooth mode. But the general rule of thumb is that for edits like this, it probably makes most sense to do most of your edits in the box view mode. There is a shortcut to switch back and forth, and I think this is super handy to know. Canceling out of this, it's Alt-1 and Alt-3. So Alt-3 is smooth, Alt-1 is box. Alt-3, Alt-1. Okay. Alt-2 does like an overlay of it's like a box mode with an overlay of the smooth. I don't think there's too much information on the screen. So let's take a look at this one in the box view mode. Okay. Because we're going to edit this a few times. The next thing I wanted to show is the edit form. This is kind of like the move command for T-splines. Okay. And this is the most useful command in the whole interface here. Okay. So this allows us to select basically anything: surfaces, edges, groups of surfaces and edges, just lines, anything, right? And you have different ways to, there's different methods in which we interact with something. So I'm just going to select a single face. Okay. And so I've got one face selected. Zoom in here so you can see what's going on there, and you can see there's a locator that sort of positions itself on the face, and it's oriented to like the Cartesian direction, right? You can change this as this is a multi-locator, so it's got scaling commands, rotating commands, translation commands, global scaling command. Like everything is there. It's kind of hectic, right? And you might have to rotate around. Like if you want to get like just a specific one, you might have to rotate around to get it. If you just want to display a specific type of editing transformation mode, you can do like this one, just translate, right? So it gets rid of the rotate and the scaling commands. Just rotation, gets rid of the other ones. Just scaling. So depending on your preferences, you can cycle back and forth between these things. Coordinate space, this one's really important. So by default, we show the world space coordinates on any of your selections. If you select more than one, it sort of puts the locator sort of geometrically in between them. But just with one face here selected, this is the view space option I'm going to switch to. Okay. And you'll notice that no matter how I rotate the model, it sort of like assumes I'm looking down an axis, right? This is super handy sometimes, right? If you want to get I just want a front view and, or some diagonal view, you can orient the edits that you're going to make to your view space. This is a really good one. The next one is selection space. This one is awesome. I use this one probably just as much as the coordinate space or the world space mode, maybe even more. So selection space orients, it's got some intelligence in there, and it orients the locator to the parts that you have selected. So this surface I've selected is at some funky angle, right? It's not really aligned to anything. But you can see that with the selection space mode on, it's got like one of these is normal to the face, right? So that is like super handy because that's an edit that I could see myself, making, right? And then the last one here is local per entity. So this is useful if you have multiple items selected. But I think the two most useful ones are, I guess really they all have use, but I guess I just got to put in a plug for the selection space one because that one just seems to be the most handy. There's some other modifications in here too. I definitely want to, or sub regions of the edit form workspace that I wanted to talk about. One in particular is the soft modification. So I've got this one face selected and I can move, push and pull this one up and down. That's all fine. But you notice it's literally only adjusting the entity that I have selected, right? So this is going to maybe result in a funky shape afterwards. Let me see if I can remember how. So I'm going to pull this up like, I don't know, 0.5 centimeters. Okay. Like that's not very smooth, right? And again, I'm in the box view mode, so I don't know, like it's probably going to get smoother when I go back to the smooth mode. Let's take a look. Go back to Alt-3. It's fine. Yeah, I mean, it's smooth, but like, yeah, you can see a little bit of an influence there, or a little bit of a transition there. So let's go back into the box mode. Let's move this one back down to where it was. So remember that I was in selection space, which is nice. I'll move it right back to where it was. Okay. Again, just double check, super smooth, right? This is the original part. And let's make an edit one more time. So I've got this face selected, and now I'm going to turn on soft modification. Okay. Now what soft modification does is it propagates out the changes that I'm making to whatever my selection is, or whatever the selection entities that I happen to have selected there. It's going to propagate those changes out to the rest of the T-spline body. You can choose like how far out you want those changes to go. Right? You can, use this to, go way out. You can keep it very localized. You can choose like a specific face count. Like maybe I want it to influence just two faces. So it's going to go outwards, two faces in every direction and have an influence. You could change the transition type, smooth, linear, like a bulge. Let me do a smooth one here, maybe two faces out. That looks pretty good. Okay, so now I'm going to move this one up the same, like 0.5. I think it was 0.5. So now, I mean, I'm in the box mode, but it already looks smoother than it was, right? So if something looks pretty smooth in box mode, you can be pretty darn sure it's going to be smooth in the smooth mode too. So now let's take a look. All right. So that same bulge that I just pulled out right there, now it's got like a much better transition in here. So just give you an idea of some of these, some ways that you can, edit these shapes. I think that, playing around with soft modification is a very important one to know. Let's talk about frozen edges. So everything in here can be edited except for regions that are frozen. So you can come and say, this region is going to freeze. So now like this little edge and, edges or surfaces around it cannot be moved. So if I try to move this one, it's either going to not let me or it's going to bark. So yeah, it's not letting me move this particular entity, right? If I try to do a soft modification, see, that edge that I had originally selected, I mean, it's locked. It's locked in there. It cannot move. We do this automatically on the region or the open edge where we intersect with preserves for good reason, because if we zoom in here, you can see that we barely interfere, just a little bit, the form, body, and all the preserves. And the reason why we do this is because that's necessary for that boundary fill operation. So in order for the boundary fill to work, we have to be touching or interfering with another body. Otherwise, there'd be a gap and it wouldn't create the solid geometry that we need for production or taking this to the next step. So we automatically freeze the edge, the open edge of all of these, form bodies or form shapes. If you want to select the entire edge, an open edge like this, you can just double click it, and it will give you that entire edge. Now you can right click and go to unfreeze. You can also find that in the modify command. So if you do want to modify these things, you do have to unfreeze them first. I just lost it. Oops, Test it again. So you have to unfreeze from here. You can freeze, refreeze. So I just froze something else over there too. So yeah, freezing, unfreezing. It's a good thing to know. Let's talk a little bit about bridges. So there is, I feel like this is a pretty good one to know. So let's make a bridge. So let's say you can see there's like this is a structural member from here to there. That's nice. Maybe I want to add another structural member, like this particular area. Oops. Like this particular member is not really touching this central member here, but maybe I want to add a bridge across that gap. So how would I do this? So you can do it in a couple different ways, but the easiest thing is to go right up here, modify, bridge, and kind of like a loft. It's very similar to lofting. You can go over here and select one face over there. Now I'm going to define my second side, and maybe let's do this one. Okay, so I've got two sides selected, the preview of what that looks like. And this is a preview of what that bridge will look like. So you can add a twist, you can change the number of faces, you do a lot of stuff here, but let's go ahead and, and sometimes depending on the order in which you select the face, you might have to like flip the direction. It might be a little like twisted on you already, but this one looks pretty good. Let's go ahead and hit OK. And I should have done this in the box mode so you can see what it looks like. Box mode looks, it looks fine, right? A little boxy, but yeah, when we switch back into the smooth mode, you can see that it sort of auto smooths out. It's kind of a sharp transition, but yeah, that's a bridge, right? That's one way to do a bridge. You don't have to do just one face. Let's do multiple faces over here. So I'm going to try this one more time. I'll do it on the other side. And I'm going to select 4 faces. And the order in which you select them is important. So I'm going to start in this corner, work my way around, and now I'm going to select sort of a landing face somewhere else. And actually, before I do that, I'm going to switch back into the box mode so you can see what it looks like from this mode as well. So again, I'll go to Modify, Bridge, and let's pick those 4 faces. And then we're going to do the second side. And I'm going to try to do it in the same general order that I did previously. And that's the best way to get these things to line up. Otherwise, you might have some funky, if you do like diagonal, and then the other diagonals, this probably won't work well unless you do the exact same order on the other side. But that's going to be another bridge. Let's go ahead and drop this one in there. So I've got a second bridge over there. So, with multiple faces, you can bridge these things. Now, if I go to smooth mode again, like that's pretty nice, right? So you can very quickly edit these geometries and add bridges if you want to add additional structural support. Let's talk a little bit about smoothing next. I really like the smoothing command. It's available in the modify pull down right down here. I like it so much I promote it to the top toolbar because I use it all the time. General rule of thumb, if you can get your box viewing mode looking smooth, then your smooth mode is going to be like just fantastic looking, right? So let's do some smoothing and see what happens here. So this is the box view mode. I mean, certain areas looks pretty smooth, especially when you zoom out, but like I made a pretty egregious edit right in here. This thing is frozen, so I'm going to unfreeze that. There we go. I think I made a weird freeze edit over here. I did. Okay. So everything's frozen, or everything's unfrozen except for my ends, which is fine. I'm not really going to deal with the ends right now. Let's start doing some smoothing. So smooth, I'm going to make sure I can select through. I'm just going to select the whole section here, maybe this whole section. So just grab the whole bunch of that stuff and watch what happens when you use the smooth slider. I'm just going to move it all the way to the right. Okay, just keep doing this. You can do it a couple times. You see what happens? It's sort of blending out any changes. Like there's, it's sort of making the model very smooth. You can see that from a distance now, this is like, that was a terrible edit I made, right? I pulled this thing out and it was really sticking out there, kind of like a bump. And now from a global overall view, this area even looks smoother than these members over here, right? So if I go back and go into the Alt-3 smooth view mode, it's just butter smooth, right? Just very, very smooth over there. possibly better for manufacturing. I guess it depends on your particular manufacturing method. Definitely better from an aesthetics point of view to have smooth geometry there. Let's do another one here. Let's go. I'm going to grab. Let's do this and check this out. So I'm going to show another little trick here. So I'm going to grab just one of these surfaces here. I'm going to hold down the shift button and hit up on my keyboard. And when you do this, actually, it's probably better to show it over here. When you hold shift and hit up on your keyboard, it sort of expands your selection space. So it goes like one element out in all directions. Pretty handy. So let's select these guys here. Okay, so I've selected sort of the middle bodies there. I'm going to do shift up, maybe one more, shift up. Okay, so now I've selected that bridge plus some of the surrounding geometry. Heck, let's go one more. Why not? Let's do some smoothing. I'm in box view mode, so you can see the impact here. Go smooth. Hit OK. Smooth again. Hit OK. Now it did some things that I might not want, but you know, it is smoothing. Maybe I needed more elements in here or more faces in there. But let's go back to the smooth mode. Now this is like, it's just really smooth, right? I'm not a huge fan of what it did in the middle, but again, this stuff can be edited also. Maybe if I want to go back and, you know, edit these things, select this ring, maybe that ring, just double clicking it. It's got some intelligence in there. If you double click, it'll find if it's like a closed loop. Let's do a scaling here and see what happens. Nice. So now back to like my original thickness. And there you go. Just did some blending there, you know. Just a good way to use the smooth command. I kind of like to use it as like a sledgehammer, just to smooth everything. Again, if you want to have your select through filter on, but yeah, just go in here and select a whole bunch of stuff. See what happens. If the edits that are required to get this smoothing algorithm, if it must unfreeze a region, it'll ask you first. You know, if you try to smooth something and it needs to, you know, move something that's frozen, it'll prompt you. You could say yes, but yeah, just give you an idea what that smooth command does. This model's it's really smooth. I mean, it was smooth to begin with, but now it's really smooth. Let's talk about hole removal next. Let's go back into the box view mode. So if you want to remove this hole, you can actually like come in here and manually delete stuff if you want. Certainly a possibility. Hit the delete button. It'll actually just remove that. That's now like an open face. If I was to exit out of this form environment, this will, I mean, there won't be any body, right? There's nothing here. I just have my my geometry because the boundary fill is no longer able to do its work because that's an open surface. Let's go back and undo that. So instead of just deleting, there's an elegant way to do this. You can come in and say, I want to select all the faces of this hole. It probably goes to the other side too. Yeah, let's get the other faces too. So we've got all of the faces of this hole or associated with this hole selected. Now let's go use the erase and fill command. And a couple options here. You can use a fill star, reduce star. I think the reduce star gets a slightly better result. Hit that button. And what it's going to do is it's going to like delete those faces and then automatically fill them in for you, right? Looks pretty good. You could definitely tell where it was. Maybe some smoothing would be advantageous here. So maybe you want to come in here and, you know, select some of these faces. Maybe do a shift up to get the next set of faces too. Let's do some smoothing, see what happens. Maybe one more round of smoothing. And there you go. So that hole's gone and it's very smooth, right? Looks like I can make a couple more edits here, but just an easy way to get rid of some of those holes if that's something that you're interested in removing. One more thing here before I wrap up on T-splines. Let's delete a couple faces here. Let's do something truly terrible. Let's delete like these 9 faces. I'm just going to do it with the delete command on my keyboard, delete button. Looks like I got one extra one. That's actually fine. If you want to create a face, this is the only thing of creation that I typically deal with. You can create a face by selecting 1, 2, 3, 4 faces. So I basically created my own face there. So if you delete too much or whatever, you can do that. But how would I fill this gap? If this is a gap that exists, what would be the easiest way to do this? One thing you could do is you could select these guys here, and I could just pull this, right? You just do one of these, right? Start pinching things together, but you can see that might lead to some funkiness right here. So instead of doing that, let's undo what I just did there. Instead of doing that, I wanted to show the Alt Add workflow. So by using the Alt Add workflow, you're able to actually extrude or add pieces as you use the editor. So let's go ahead and open up the edit form. And now as I drag this forward, I'm going to use the Alt button or hold the Alt button. And instead of moving the geometry, it just like extrudes, right? So it's not really influence. It's not moving. It's doing extrude instead. Okay. So I'm going to do 1. I've Alt is still held down. 2, 3. Okay. So I've got a little bit of work to do here, but check it out. I mean, that's like, it's way better than like manually closing this hole off, right? So using this extrusion command is pretty nice. So now I'm going to like use another command here, and I'm going to merge edges. Okay. So I'm going to select my first edge group. That's the one that I'm going to move. I'm going to select my second edge group. This is the one that is going to move to. Hit OK. It's fine. And you can see it's starting to build this out at this point. And now I need to close off the rest of it. Let's go use the merge edge one more time. 2, 3. And then the other one is inside here. 1, 2, 3. Hit OK. And you can see that it's starting to close that shape off here. Got to do a little bit more cleanup there to get that one fully closed. But you can use that merge edge command to very quickly patch a hole, either that you made yourself, or you might want to if you're trying to bridge a gap instead of going through and explicitly creating geometry, which can be time consuming. You can just use that merge edge command to snap things together. So hopefully this gives a pretty good preview or a pretty good overview of some of the more basic T-splines commands. And like I said, there's some decent documentation on learning some of these more detailed T-spline workflows, but for modifying generative design form bodies, we don't need everything, but there's definitely some good ones in here. So hopefully, if you guys have a chance, you can look at some of the other training material. All right, last topic. Appreciate everyone hanging in there this long. T-spline. The section was a little lengthy there, but one last little tip here, and I think it's a pretty good one. So sometimes we want to hollow or shell a component. Maybe it's for, I don't know, injection molding, or maybe it's to put a lattice inside a component. There's a lot of reasons why you might want to do this. Save some material weight. Let's talk about how to do that with a generative shape. Okay, so I'm going to jump right into Fusion here. So this is one of the outcomes. One of the I believe it was an unrestricted. It might have been one of the CAM, like 3 or 5 axis outcomes from the triple clamp, the motorcycle triple clamp example, again, in the example section of your Fusion interface. But let's say you wanted to shell this. Like, how would you do this after the fact, right? You could use the traditional shelling command. If I do a little cross section here, you could come through and actually shell this. It's 0.1 millimeters. 0.25, but then, how would I go about, you might have to do some edits here. Like, yeah, I could shell this, but then I'd have to re-solidify this. And sometimes these resultant shapes, they're very complex to the point where like shelling doesn't even work. right? So for instance, if I want to do like a shell size of 1 millimeter, it's not going to let me do it because of the complexity of the shape on the inside. So how do we do this, right? One way to do it is to go back to the original form body and make the shell there. So let's show what that looks like. So I edit the form body. So now I'm in my T-spline or form workspace here. You can actually copy this shape and create a new one. So watch this. I'm going to go right click organic one, copy, paste. So now there's the next one in here. Let's call this one shell body. So now I've got two form shape or two form bodies in here. And what I'm going to do is I'm actually going to select the shell body, go up to modify and thicken. Okay. So this happens at the form level, not the like design level. So this is like, you know, no matter what I do here, this is pretty much going to work. And I'm actually going to thicken to the inside. Let's go -1 millimeter. Okay. Something that we couldn't do before. So let's go ahead and do that. So now I have two shapes here. I've got the original form shape, and then I've got a shelled shape, and this is like a solid now. Like I did that thick. This is a solid, so this will interface very, very nicely with my preserved geometry. Let's go ahead and exit out of the form environment. Okay, so now I have a shell body, which is a solid, and I have the original, that body 12. That was like the original geometry, all solidified together. So how do I what do I do next, right? So one thing you can do is you can go back to, let's go back in time, literally going back in time in the timeline. I'm going to go back before the form body, okay? And what I needed to do is grab the preserves, so preserve 1, 2, and 3. Just going to cut and paste them, copy, paste. So now I have carbon copies of preserve 1, 2, and 3. That's all I need to do. Go back forward in time. And now, the cool thing is none of this edits. None of this has any impact on like what I did with the form body or what I did with like body 12 and how that was built with a like a boundary fill. It doesn't impact any of that. It just adds more bodies to work with here. So let's get rid of body 12, make that invisible because I don't really care much about that one right now. And let's do a combine. Let's combine shell body with my solid preserves. Okay, now I have shell body, and this is now a true shelled out component, right? And it's super elegant. It's fully editable by going back into the form workspace. If you wanted to come in here afterwards and, you know, maybe add some stress relief, everyone likes adding stress relief. You can very easily do this. Yeah, it's really cool. Really cool method to making a shelled component. If you wanted to say take the inner space in here, so let's cut this from a different angle. Maybe you're a NetFab user and you care about this inner volume. You want to take this inner volume and perform some like latticing operations on it or whatever. You know, this would be a good opportunity to maybe use the boundary fill command. So now I can come in here and say modify or create boundary fill. I'm going to select, this is my tool body. I'm going to select a couple cells here. Maybe I just want the inside piece, which would be that one. I don't want to remove tools. This is going to create a new body. So now let's get rid of shell body. And now this is that inner space, right? So I've used that boundary fill command, the same one that we used to make make that combine feature, combining a really complex form body or T-spline body with preserves. You can use the same thing to create that inner wetted volume. So just a neat little tip on how to make shells or how to hollow out a part. Definitely do it at the form body level. Don't do it at the design level because it's much more robust. You have a lot more control over it. It's fully reliant on that original T-spline form shape. Just a more elegant way to do shells and hollowing. All right, we made it. And with that, I will go ahead and conclude this tips and tricks session. I appreciate everybody sticking with me to the end here. This went a little bit longer than I had originally planned, but there's just so much content to cover. If you have any questions or want to reach out, feel free to send me an email. I'd be happy to get in touch with anyone. If you want to sit down and have a chat about a specific application or problem, totally happy to do that for you. Hope you enjoy the rest of the Manufacturing Summit sessions, and yeah, have a good day. Thanks, everyone.